The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. So today we're going to continue reviewing. We're going to look at chapter 9. Tomorrow we'll look at chapter 10, and if you do the math, after tomorrow there's no more reviewing, which means I won't be doing a chapter 11 session online, but you can always go back and look at the chapter 11 videos, or you can come to my office hour today or tomorrow at 1:15 if you have any questions about chapter 11. Anyway, with that in mind, we're going to go on and take a look at chapter 9. As I've said, if you have any questions as I'm going along or need to slow down or anything, please let me know. So here we go. This is section 9.1, radical expressions and radical functions. So this is where we started looking at square roots. For instance, the square root of 49 is 7. The quantity inside is called the radicand. This symbol here is called a radical. And let's say we have the cube root of 8, which is 2. This number is called the index. If you're taking a square root or a second root, the index is an implied 2, but is not necessary to be written. But any other index, you do have to write it, whether it's cube root or fourth root, etc., etc. Let's see here. You cannot take a square root of a negative number. You can't take an even root. In fact, let's put even here. So if the index is even, you can't take like a second or fourth or sixth or eighth root of a negative number and get a real answer. So this is going to be not real. Also, when you take the square root of a number, you get a positive answer. You can't take the square root of a number by itself and get a negative answer. And this positive number is called the principal square root. Just a little review of some vocabulary there. Let's see here. Let's take a look at dealing with something like absolute value. Let's say we've got the square root of 64, what is that, t squared. And we are told that t can be any real number, or as the author in the book says, it's unrestricted. So t can be positive or negative or 0. Well, in that case, the square root of 64 is 8. The square root of t squared is t. But if t is a negative number, we would be giving an answer involving a negative number. So what we need to do is put absolute value bars around the variable to assure us that it is not a total negative answer. Now, let's say we've got the cube root of 64t cubed. Well, the cube root of 64 is 4. The cube root of t cubed is t. When you're taking a cube root or any other odd root, you can get a negative answer. So here, we don't need absolute value bars. In fact, putting them would be incorrect. Any questions about that situation? Let's talk about domain. We've looked previously at something like f of x equals 1 over x minus 3. And we said that x can't equal 3 because f of 3 would be 1 over 3 minus 3, which is 1 over 0, which is undefined. So here, the domain would be all real numbers except 3. And that would look like that. Okay, so that's dealing with the denominator can't be 0. But now we've got a new situation, and that is, let's say we've got something like this. G of x equals the square root of x plus 12. And it asks for the domain of the function. Well, just a few minutes ago, I mentioned that you can't take an even root of a negative number. Since we're taking a square root, the radicand inside the x plus 12 can't be negative, which means it either has to be positive, that is greater than 0, or equal to 0. So if we're looking for the domain of a radical function that has an even root, we take the radicand and set it greater than or equal to 0. Then, solving this inequality, we get x is greater than or equal to negative 12. Writing that in interval notation, let's see, we would start at negative 12 and go on forever to positive infinity. Any questions about that situation? Okay, let's see here. What about something like this? Find the fourth root of 81. If you can't just sit there and go, oh yeah, that's 3, what you can do is you can take it and break it down using prime factoring. So this is the same thing as the fourth root of 3 to the fourth. Recall that when the index matches the exponent, okay, and the base is positive, you can just bring the base out front. Or what I said during this chapter was the nth root of a to the n power equals a if a is greater than or equal to 0. All right. How about this? The cube root of negative 27. Now be careful. Yes, I said you can't take an even root of a negative number, but you can take an odd root of a negative number. This would be negative 3 because negative 3 cubed is negative 27. Let's see here. I think that's all I want to do in this. I want to get on to section 9.2. And section 9.2, we talk about rational exponents. We've got all these rules of exponents, and we've applied them in the past to whole numbers and integers, including 0 and negative numbers. Now we're going to apply them to fractions. So let's say I've got the cube root of 8, okay? Its exponential equivalent form would be 8 to the 1/3 power. The index becomes the denominator of the exponent, and both of these are equal to the number 2. Let's say you've got the cube root of, let's see, 4 squared. That would be 4 to the 2/3 power. The power inside is in the numerator of the exponent. The index is in the denominator. Okay. Now, when you have something like this, you can either do the power first and then the root, or you can do the root first and then the power, as long as they're both defined. Okay. Let's see here. What about this? 27a cubed b cubed all to the 2/3 power. So I have a product raised to a power on the outside. I'm going to take that each factor inside and raise it to that outside power. So we get a 2/3 exponent on all the bases inside. Okay. Now, 27 to the 2/3 power, I could take the cube root first. The cube root of 27 is 3, and then that squared would be 9. So 27 to the 2/3 power is 9. A cubed to the 2/3 power, you would multiply the exponents. 3 times 2/3 is 2, so this is going to be a squared. And the same thing here, b squared. So 9a squared b squared would be your final answer. All right. Let's see here. This says change each radical to an exponential expression. The 7th root of 7p squared q. So that would be 7p squared q, all raised to the 1/7 power. Okay, again, the index becomes the denominator of the exponent. Let's go the other direction. Let's say we have, where is it here? There we go. The quantity 7a squared b squared to the 1/5 power. Changing that into radical notation would be the 5th root of the quantity 7a squared b squared. And here in this problem, they're not asking us to simplify it, just to change it to the other form. Recall, if you have a negative exponent, you can change that to 1 over that base to a positive exponent. And 49 to the 1/2 power would be like the square root of 49, or 7. Let's see here. 4 to the 2/5 power times 4 to the 2/5 power. When you're multiplying two powers with the same base, you take that same base and you add the exponents together and then attach them to that base. So you get 4 to the 4/5 power. Let's see here. Let's say we have 5 to the 1/3 power times 5 to the negative 5/3 power. This would be 5 to the 1/3 plus negative 5/3 power, which would be 5 to the negative 4/3 power, which would be 1 over 5 to the positive 4/3 power. Again, any questions on how that works? Okay, let's say we've got 2 to the 5/6 power times 2 to the 1/3 power over 2 to the 1/2 power. Well, in the numerator, multiplying powers with the same base, you would add the exponents. So our exponent becomes 5/6 plus 1/3. But 5/6 plus 1/3 would be 5/6 plus, we're going to multiply 1/3 by 2 over 2 and get 2/6, which is 7/6. So this would be 2 to the 7/6 power in the numerator. Okay. Now, dividing two powers with the same base, you take that base and attach the difference of the exponents, the top exponent minus the bottom exponent. Well, 7/6 minus 1/2, you'd multiply 1/2 by 3/3, and you'd get 4/6, which reduces down to 2/3. So final answer, 2 to the 2/3 power. Any questions there? Alrighty. Let's say we've got y to the 2/5 power times the quantity y to the negative 2/5 power plus y to the 3/5 power. So here we're going to distribute. We're going to get y to the 2/5 times y to the negative 2/5 plus y to the 2/5 times y to the 3/5 power. Multiplying powers with the same base, we add the exponent. So this would be y to the 2/5 plus negative 2/5, which is y to the 0, which is 1, not 1y, but the number 1. Here, multiplying two powers with the same base, adding the exponents, 2/5 plus 3/5, which would be y to the 5/5, which would be y to the 1, or we could just say 1 plus y because there's an implied 1 exponent on the y when there's no exponent written. Okay. let's say we've got this, the 6th root of 7 cubed. It says use rational exponents to simplify each radical. All variables represent positive real numbers. So if we rewrote this in exponential form, it would be 7 to the 3/6 power. Keep in mind the index goes in the denominator and the power goes in the numerator. But 7 to the 3/6 power is 7 to the 1/2 power, which would be the square root of 7. So we're taking this and reducing it down to that. What's happening? We're just taking 3 divided by 6 and reducing it down to a 1 divided by 2. But we don't have to write the index or the 1 exponent. They're implied. Let's see, how about something like this? The 4th root of the square root of x. Well, that would be the square root of x to the 1/4 power, which would be x to the 1/2 power to the 1/4 power. So I'm changing all the radical notation into exponential notation. But when you have a power raised to a power, you multiply the exponents. 1/2 times 1/4 is 1/8. So finally we get the 8th root of x. So we're taking this and changing it into that. Okay. I think with that, I'm going to go on to section 9.3. Again, if you have any questions of something I'm doing, feel free to stop me. Otherwise, I'm just going to zip along. Let's see here. This is talking about simplifying and combining radical expressions. Let's say we have the square root of 28. To simplify this radical, we want to take everything we can from inside to the outside of the radical. Since the index is a 2 or an implied 2, if we can find factors inside that are squares, we can unsquare them, take the square root of them, and kick the bases outside. This would be equal to the square root of 4 times 7. But the square root of 4 is a 2 on the outside. The square root of 7 doesn't come out nicely, so the square root of 28 simplifies into 2 square roots of 7. Again, simplifying doesn't necessarily mean it looks nicer, but we've got less inside the radical. All right, let's say we've got the cube root of 40. Now we're looking for factors that are cubes. Well, 40 is 8 times 5. 8 is a cube. The cube root of 8 is 2, so I've got 2 cube roots of 5. Now, what if you can't just look at 40 and see that, oh yeah, 8 is a factor and it's a cube? What could you do? You could take 40 and you could break it down using prime factoring and say, oh, it's 2 cubed times 5. So then you could say, well, this is 2 cubed times 5, but the cube root of 2 cubed is a 2 on the outside, and we arrive at the same answer. So if you can't just see it, you can work it out. Okay, let's see here. Let's say we have a fraction inside of a radical. We can separate the numerator from the denominator and have the division of 2 fractions. Well, from here, the square root of 4 is 2, so I can simplify it in that way. You can also go the other direction. That is, if you have a radical divided by a radical, as long as the indexes, or is it indices? I'm not sure what the plural of index is, but if they're the same, you could rewrite that as a single fraction under a radical. And then inside you could reduce it and arrive at an answer that way. Okay. Let's see. Simplifying by combining like radicals. 11 square roots of 3 plus 2 square roots of 3 would be 13 square roots of 3. because you've got 11 of something plus 2 of something equals 13 of that same something, the something being the square root of 3. Okay, now what about this? 9 plus the square root of 45 plus the square root of 20 plus 16. Well, I can see how I could put the 9 and 16 together, but the square root of 45 and the square root of 20 don't look at all alike. However, if we simplify, let's take the square root of 45, which we could write as the square root of 9 times 5, and the square root of 9 is 3. So the square root of 45 becomes 3 square roots of 5. And then if we take the square root of 20, which is the square root of 4 times 5, the square root of 4 is 2, so we get 2 square roots of 5. Now we can put these together and those together. So the key there is to simplify each radical as much as possible, and then look and see if we can combine any like radicals. Okay, let's see here. One more of those. The square root of 20 plus the square root of 125 minus the square root of 80. So we just did the square root of 20 a little bit ago, 4 times 5, so that's 2 square roots of 5. Then the square root of 125 would be 25 times 5. The square root of 25 is 5, so we get 5 square roots of 5. And then the square root of 80 would be the square root of 16 times 5. The square root of 16 is 4, so we get minus 4 square roots of 5. 2 plus 5 is 7, minus 4 is 3 square roots of 5. Any questions there? Okay, let's see here. How about, I think we're going to go on. So we're going to go on to section 9.5, which is solving radical equations. So let's say we've got this. The square root of x minus 10 equals 1. If you're trying to solve an equation with one term that's a radical, you want to isolate that term, move everything else to the other side of the equation, and then we can square both sides because it's a square root. Squaring the square root gets us, they basically undo each other, so we get x minus 10 equals 1 squared, which is 1. Adding 10 to both sides, we get x equals 11. Let's check our work. If x equals 11, we've got that, which is that, which is that, so it checks. Any questions there? No? All right. Let's say we've got the square root of 1/2 x plus 3 equals 6. Again, the radical should be, and already is, isolated. So we'll square both sides of the equation. We get 1/2 x plus 3 equals 36. Solving for x, we'll subtract 3. 1/2 x equals 33. Multiply both sides by 2, and x equals 66. Let's check our work. And so we get this. 1/2 times 66 is 33. 33 plus 3 is 36. The square root of 36 is 6. 6 equals 6, and the answer checks. Okay, let's see here. Now, let's say we've got the square root of 3x, and then plus 5 outside of the radical equals 2. Again, we want to isolate the radical, so we'll subtract 5 from both sides, and we get that. Now, Squaring both sides, we get 3x equals 9. Divide by 3, x equals 3. When we go to check our work, we get the square root of 9 plus 5 equals 2. 3 plus 5 equals 2. 8 equals 2. This does not work. This is what's known as an extraneous solution. And if I recall correctly, what will happen in WebAssign is they'll ask you to find the proposed solutions, and then you go back and check. And so in this case, you would say that depends on how it asks it. It might say if there's no solution, write it, or it might say find potential solutions, and then is it extraneous or not, meaning it doesn't work. Okay, so again, read the directions carefully. While I'm thinking about it, when I was going through and correcting your last test, chapter 11 test, quite a few people missed problems because I think they just didn't read the directions. It would say something like, round the answer to the nearest 100 or to the nearest 100th or something like that. And students, the numbers they had were correct in their calculations, but they didn't do that last step of rounding the way the question was asked. So be careful to read the questions, to read them fully. Okay, let's see here. How about this? The cube root of the quantity 12m plus 4 equals 4. Again, we've isolated the radical. However, it's not a square root, it's a cube root. So we're going to cube both sides of the equation, which gives us 12m plus 4 equals 64. Subtracting 4 from both sides, 12m equals 60, divided by 12m equals 5. Let's check our work. This is 12 times 5 plus 4 equals 4. Cube root of 60 plus 4 equals 4. Cube root of 64 equals 4. 4 equals 4, so it checks. If we have a situation, let's see, that looks like this, 2b plus 29 to the 1/3 power equals 3. Well, 1/3 as an exponent is like a cube root. So again, we'll cube both sides. Power raised to a power, you multiply the exponents. 1/3 times 3 is 3/3 or 1. So we get 2b plus 29 equals 3 cubed, or 27. Subtract 29 from both sides. 2b equals -2. Divide by 2b equals -1. Let's see, we'd have 2 times -1 plus 29 to the 1/3 power equals 3. -2 plus 29 to the 1/3 power equals 3. 27 to the 1/3 power equals 3. Cube root of 27 is 3. So again, the solution is correct. If you have a situation with two radicals, you want them on opposite sides of the equation. So kind of the same thing we did back in, let's see, it was chapter 8 where we dealt with absolute value. I think we did that, where if you have one absolute value, you want it by itself, isolated on one side. If you have two, you want one on each side. Same thing here. If you have one radical isolated on one side of the equation, two radicals, separate them. So now I'm going to square both sides, and I get m plus 4 equals 2m minus 5. I'm going to solve for m on the left. I'll subtract 2m from both sides. So I get -m plus 4 equals -5. Subtract 4, -m equals -9. Divide by -1, m equals 9. Let's see what happens here. We get 9 plus 4, 2 times 9 minus 5, 13, 18 minus 5. All right, I don't know off the top of my head what the square root of 13 is, but I know it's real. And the square root of 13 is equal to the square root of 13. So my solution x equals, or excuse me, m equals 9 is correct. Let's see. Let's solve a formula. Let's say we've got D equals the cube root of the quantity 12v over pi. And we are to solve for the letter V. V is locked up inside of a radical. So to get it out, I'm going to have to cube both sides. On the left side, I get D cubed. On the right side, I get 12v over pi. I want to solve for V. So I'm going to multiply both sides by pi. So I get pi d cubed equals 12v. Then I'll divide both sides by 12. So v equals pi d cubed over 12. All righty. Any questions there? Well, you know what? I've got some, well, no, let's do one more. And then if we've got a few minutes, I'm going to go ahead and actually start chapter 10. Maybe we will get to chapter 11 tomorrow. We'll see. We'll see. Let's say I've got this situation. It says, let s of t equal the square root of t plus 8. And h of t equal 6 minus, hang on. Nope, my bad. We can't do that one. Sorry. Let's see. Here, we can do this one. Sorry, that takes us in a place where we don't know how to deal with it in this class. Let f of x, so let f of x equal the fourth root of x plus 8 minus the fourth root of 2x. Find all values of x for which f of x equals 0. So basically, we're going to set this whole thing equal to 0. So we're going to get 0 equals that. I've got two radicals. I want to separate them. I'm going to add the fourth root of 2x to both sides. So now I've got the fourth root of 2x equals the fourth root of x plus 8. See how that worked out? I'm going to take each side and raise it to the fourth power. So 2x equals x plus 8. Subtract x, x equals 8. Let's check our work. 0 equals the fourth root of 8 plus 8 minus the fourth root of 2 times 8. That should be, let's see here, the fourth root of 16 minus the fourth root of 16. Well, again, the fourth root of 16, let's see, what is the fourth root of 16? 2, 4, 6, 8. Oh, that's 2. And even without simplifying this, they're the same radical. So 1 minus the same thing would be 0. So one of them minus one of them is what I'm saying. Okay, let's go on to chapter 10. And let me get started here. So we're going to start chapter 10, and we're going to take a look at section 10.1. And as I say, we'll get as far as we can, and we'll pick it up tomorrow. 10.1 was using the square root property. So if you had something like w squared minus 47 equals 0, you want to write it in such a way that on one side you have a square containing, we're going to say with a variable in it, and over here you're going to have some number. Okay, so how am I going to get there? Well, I'm going to add 47 to both sides. W squared equals 47. Then I'm going to take the square root of both sides. But when you've got an equation with a variable involved, you've got to apply a plus or minus to the square root of 47. So w equals plus or minus the square root of 47. Recall two things. One, I can't simplify the square root of 47. If I could, I would. WebAssign, I don't think has a way to put in a plus or minus. So you're going to have w equals negative 47, w equals negative the square root of 47, w equals the square root of 47. Okay, so you're going to write those answers separately. It may even have you do it like separating them with a comma, but it doesn't have that plus minus ability. Okay. Let's say we've got something like this. U squared minus 24 equals 0. So I'm going to get it in that form I want, which is that. Taking the square root of both sides, we get this. However, the square root of 24 is the square root of 4 times 6 is 2 square roots of 6. So this becomes plus or minus 2 square roots of 6. So u equals negative 2 square roots of 6, comma, 2 square roots of 6. There would be your two answers. So you're expected to simplify any radicals that you can. Alrighty, let's see here. If I have x minus 1, the quantity squared equals 4. That's already in that special form where I've got a perfect square containing a variable on one side of the equation and a number on the other side of the equation. So I'll take the square root of both sides, apply the plus minus. So I get x minus 1 equals plus or minus 2 because the square root of 4 is 2. But I haven't solved for x yet. I've got to add 1, so I get x equals 1 plus or minus 2, which means x equals 1 plus 2, which is 3, and x equals 1 minus 2, which is negative 1. So x equals negative 1 and 3, or 3 and negative 1. Okay, here. Let's see. This says, let f of x equal x plus 3 squared. For what values of x is f of x 7? So for what value or values of x is f of x equal to 7? That's supposed to be f of x in there. So basically what we're looking at is solving that because we're making 7 go in the place of f of x. That's good to go. We'll take the square root of both sides. X plus 3 equals plus or minus the square root of 7. Subtract 3 from both sides. X equals negative 3 plus or minus the square root of 7. So x is negative 3 plus the square root of 7. X is negative 3 minus the square root of 7. So there's your two solutions to that problem. Okay, we're going to go on to section 10.2, which is the quadratic formula. This is a formula that you should have memorized. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And how would we apply that? Well, let's say we've got the following equation. 6x squared minus x minus 1 equals 0. This is in standard form. That's ax squared plus bx plus c equals 0. So a is 6, b is the implied negative 1, and c is also negative 1. So plugging these quantities into this formula, we get x equals negative b plus or minus the square root of b, the quantity squared, minus 4a c all over 2a. Simplifying, we get, let's see, negative times negative, that'd be 1 plus or minus the square root of 1 plus 24 over 12, because negative times negative is positive. And that's going to be 1 plus or minus the square root of 25 over 12, which is 1 plus or minus 5 over 12, because the square root of 25 is 5. So x is 1 plus 5 over 12, which is 6 over 12 or 1/2. X is 1 minus 5 over 12, which is negative 4/12 or negative 1/3. So x equals 1/2 and negative 1/3. Okay, let's see here. Here's another second degree or quadratic equation. 2x squared plus 7x equals negative 1. To apply the quadratic formula, we need to put this in standard form. So we'll add 1 to both sides, which gives us 2x squared plus 7x plus 1 equals 0. So now we have a equals 2, b equals 7, and c equals 1. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative 7 plus or minus the square root of 49 minus 8 all over 4. X equals negative 7 plus or minus the square root of 41 all over 4. Well, we can't take the square root of 41 and get a nice answer. We can't simplify. There's no perfect square factors in there. So our two answers are going to be x equals negative 7 plus the square root of 41 all over 4, and x equals negative 7 minus the square root of 41 all over 4. Now, let's do some decimal approximations to the nearest hundredth. So we're going to punch this into the calculator. And recall, we're going to need to group the numerator so that we divide the whole thing by 4. So I'm going to have parentheses, negative 7 plus the square root of 41, which I'm going to close that up because there's a set of parentheses around the 41, and then close the whole thing up, divided by 4. And when I do that, I'm getting negative 0.149. So rounding to the nearest hundredth, that would be negative 0.15. And then the second one, parentheses, negative 7 minus the square root of 41. And again, I'm going to close up the square root of 41. You close up the entire numerator. And I get negative 3.350. So again, rounding to nearest hundredth, we would get that. Okay. That takes us to some story problems, and I think I'm going to stop there because they tend to take a while. So tomorrow we'll pick up in section 10.2, applying the quadratic formula to story problems, and we'll get as far as we can. Maybe we'll be able to get into chapter 11 some, but that's all I have for now. And if you have any other questions about this and you want to come to my office hour today, I will be there at 1:15. Otherwise, I'm going to stop the